Hi, everybody. I'm going to mute myself for a second here while y'all do the warm-up because I'm eating and I hate disgusting mouth noises on microphones. I made avocado toast for like snack or whatever, and it took me a little bit longer than I thought to poach the eggs. So I just finished and I didn't have time to eat it yet. Item number 1. I have kind of a Atwood's machine type setup. Technically, it's not an Atwood's machine because the left-hand side isn't dangling freely. But I have 2 carts here where object A has some mass. We would just call it mass A or whatever. It's actually irrelevant. But it's a block and it's sitting on a surface and it has friction. And then block B is hanging off of the edge. They are tethered together by a string that goes over a pulley. The pulley is also of negligible mass. The string is of negligible mass. All I want today is what is its free body diagram? And then item number 2, what is the free body diagram of the moon? Kind of straightforward, both of these questions, but I'm looking for 3 free body diagrams here. Label the most relevant forces for these systems, where I have block A, block B, and then take a guess what the most relevant forces are for the moon. Take a few minutes and then we'll go over this together. And then today we're going to get back into our crash course review of every major topic in mechanics and kinematics with some of the interconnections to later more complicated topics tossed in, just to make sure that we have a good inventory of all of the stuff we are expected to know about the motion of objects. How's it going out there?
Good.
Good.
How's your cat? Okay.
Surgery went well, and so I'm picking him today at 2. And if I have to bail off, like if I pause the video or whatever, it's because I'm answering a phone call from the vet. Though he just had surgery, so he's going to be a sad boy for a while. We have to keep him in a box and monitor going to the bathroom and give him medicine, all of which he'll hate. And I actually think the worst part of it is that, like, he's not. Marianne, are you signing on with a second device?
Yeah, I'm trying to get in from my computer because I'm using my phone right now.
That is fine. I just wanted to make sure because today in first period, somebody gave the class invite to a homie who tried to log in, but then they found out that I have waiting room set up, so I saw their stupid name on the thing and I never let them in. Anyway.
Thank you.
Yeah, I just hope it goes without saying, hey, don't do that. And if you do that, I hate you. Yeah, so I got to go get him at 2. I also think I'm going to go buy a bigger carrier for him just because the cat carriers I have are basically the same size as the cats because they're only in there for transportation. But if he has to stay inside of a kennel for a while, I might go get him like a bigger kennel so that he can hang out in it the next 2 weeks.
Why do you have to get the surgery?
Because he's a moron and he eats string. And the last time he ate a piece of string, we were able to take him to the vet and he threw it up. But this time, since all of our local vets were closed, we weren't able to get him to a vet. We had to take him way out of town to this place that's like a half-hour away. And by the time we got there, he had digested the string too far to just throw it up. So they had to do surgery to remove it. And the worst part about this is, like, man, if you had a kid that did something dumb and like got hurt and you had to take them to the hospital and all that stuff or whatever, like, because they're humans, you kind of have the rationale of like, oh, touch hot stove, oh my god, burn, touch stove, bad, don't touch stove, right? Animals just fundamentally don't have that same relationship in their brains of cause and effect. So I'm sure he's not going to understand that, like, oh, I got sent away and I woke up and I hurt now. And he'll never come full circle and be like, oh, it's my fault. So there's no point in like being mad at him, you know? He doesn't get what he did to himself, which is like one of the most frustrating things about raising a pet, of like they just can't understand. But oh well, that's literally why I pay every month for health insurance on the cats, so that if you have to do something expensive like a surgery, it won't like break my bank account. It's only like the cost of the copay plus 10% of the procedure. So it'll only end up being like $1,000 instead of being $10,000.
Yeah.
But I would bankrupt my entire kingdom for those cats. I would spend every dollar that it took to keep them healthy. I do not care. But for real though, if you end up ever having a pet, I highly recommend finding health insurance for them because it can totally save you in times when they need expensive procedures.
Wait, how many cats do you have?
2.
Oh.
So how is everyone?
Good. Good. What about you, Alex? How are you?
So lucky.
Great.
Quarantining, you know?
Quarantino.
Yeah.
Any additional college information? Anybody know if they got into UC Zoom?
I think we all did. Which is good.
Okay, let's go ahead and jump right into this. Item number 1, I want free body diagrams for both of the blocks in this mechanical setup. So let's start with block B. That should be easier. What forces here act on block B?
MG.
MG and tension.
MG.
Okay, and which one is bigger?
MG.
MG.
So that is to say the weight of G pulls it down, and then there is going to be some retarding friction. I'm sorry, there's going to be some retarding tension. And then what about the free body diagram for block A? What all goes on here?
MG, normal force. Force, yeah. Intention.
Okay, so we have the mass of A, G. It has its own weight, and it's not flying through the table or flying into the sky. So there must be some normal force, which is equal and opposite in magnitude. I'm sorry, I didn't do a very good job of that. Let me make the weight a little bit longer so that it matches the normal force length a little better. What other forces are here?
Tension.
Tension.
It has tension, which is why the block is most likely going to slide to the right. And are there any other forces here?
No. Mm.
Why is the tension longer?
Theoretically, this tension should be exactly the same length as this tension.
Oh, okay.
There's no friction, right?
Sorry?
There's no friction, right?
There is friction, which is what
There is?
this means. Mu is not equal to 0.
Oh, not equal to 0. Oh, okay.
Yeah, so if mu was equal to 0, then yeah, there would be no backwards friction vector. But if this thing were set in motion, it's unambiguous. It's going to move to the right as block B falls. And so the friction will always oppose the potential direction of motion. And so we would have backwards here some negative F mu, which we could also call mu m G. Those two there are equal. Those would both be valid labels. The force due to friction, which is in this case friction multiplied by the normal force, and the normal force is the same size as the weight. And so this is correct. This would receive full credit, but we have a few things to talk about here. The main one is, what is the condition that would allow this system to move or not? There's really just like 2 scenarios that could happen here. One where everything moves and one where nothing moves. What would be the differentiating factor there?
If nothing moves, would there not be any friction?
If nothing moves, there still is friction, and that is actually exactly what would stop everything from moving.
Oh.
So if there was enough frictional force, which is to say, if the friction on block A was enough, if it was big enough, if mu, mass of A, G, was equal to what? What would be driving the system to the right?
The tension.
That's what would drive block A to the right, but what would drive the entire system to the right?
Gravity.
Gravity acting on which block?
B.
B.
There we go. If the frictional force was equal to the weight of block B, then there would be no motion. That is to say, if there was enough friction on block A attaching it to that table, such that it was enough to resist all of the weight of B, and this is easy to imagine if you think of A as being very large and on a rough surface, and block B is just a paper clip or something else with a very, very, very tiny, tiny weight, you could imagine that that won't be enough weight to shift block A, right? And so if the frictional force is equal to the weight, then there's going to be no motion, and it also allows us to set a couple other vectors equal. If these two are equal, if friction is equal to the weight of B, what else is going to be equal in this scenario? Don't think about the system in total, think about each object. If there is no movement, what two forces would have to be equal here?
Tension and gravity.
Very good. If this is true, if we are in this no motion scenario, not only can we say this, but we can also say that both of these will be equal to the tension as well. That makes it so that the overall forces on the whole system in total add up to 0, but also the forces for each subsystem then add up to 0. Man, I got freshly cracked black pepper in the back of my throat. It's fine. It's a good problem to have. Delicious avocado toast. Anyway, yeah, these all become equal, and this makes it so that left and right forces add up to 0. Block A doesn't shift. Right here for block B, forces up and down equal to 0. Block B doesn't shift. Scenario 2 is the one where we do have motion, and that means that in the scenario where we do have motion, mu mag, the friction is less than the weight of B. So this is the one where we do have motion. We have some sort of acceleration on the system. And again, this allows us to make a couple of inequalities. If there is motion, is block B going to move up or down?
Down.
It is going to move down. So which force is bigger, the weight of B or the tension?
The weight.
The weight.
So this is telling us that the tension has to be less than the weight so that the weight wins and it moves down. And then up here, which way does block A move, to the left or to the right?
Right.
Right.
To the right. And that means that the frictional force in total has to be less than the tension so that it wins. And all of this information about what is the ranking of the magnitudes of these forces based on how much motion there is or isn't, all of this is discernible from the free body diagram. Now, we could calculate the tension should we be asked to do that. It's non-trivial. You'll have to go through 2 steps of calculations. The first thing you would have to do is you'd have to calculate the acceleration of the entire system. And once you had the acceleration of the entire system, you could then apply that to the motion of a single block. And then that could tell you what the tension is explicitly in terms of equations. It's a great calculation, and we've done it before, so I won't do it again. Item number 2. I would like the free body diagram of the moon. And so what is the free body diagram of the moon? What do y'all think are the most important forces acting on the moon right now?
Gravity.
Gravity? So when we talk about forces, we want to talk about between object A and B. So the gravity of the moon with what?
Earth's
Relative.
gravity.
Earth.
Okay, so the biggest force which acts on the moon is weight of the moon in the direction of the Earth. So I'm just going to draw a big long arrow here and say, hey, this is towards the Earth. And what other forces do you think act on the moon that matter for its orbit based on what you know about gravity?
Net force?
Net force is not itself a force.
Oh,
Keep in
well.
mind when it comes to attributable, hold on, when it comes to attributable forces, right, the forces have to come from somewhere. So here it's weight and weight, And then the tension comes from the string, and this tension comes from the string, and this normal force comes from the table, and this friction comes from the interaction of the block with the table. However, things like net force or centripetal force are not pure forces out in nature because they don't come from somewhere. The net force is just what you get if you take all of the forces in a system and add them up.
Okay.
Is there electromagnetic force?
Technically there is, because the moon is made of atoms, just like everything else is, and atoms have distributions of charges within them. So the electromagnetic force interaction between the Earth and the moon is not zero. However, it's basically zero because if you add up all the charges of each one of those objects, they add up to zero in total. In any given place, there's usually an equal number of protons and electrons, which is why the electromagnetic force isn't what drives orbits. Over very large distances and large collections of particles, the total electromagnetic force typically adds up to zero.
Okay.
The other force that I'm digging for here is also gravity, but what is the other thing which would have significant gravity in the hint, hint, solar system?
Other planets.
The sun.
Oh, the sun.
And do you think that the force from the sun is bigger than or less than the force due to the Earth?
Bigger. Actually, no.
Bigger or smaller?
Smaller.
Let me ask you this. Does the moon orbit the Earth, or does the moon orbit the sun?
The Earth.
It orbits the Earth, which means the Earth is the dominant thing in its gravitational field, which means that the other significant force here is, yeah, it's going to be the force due to the sun. The sun also has its own significant gravity, but it is going to be smaller than the force of the Earth. So this is always going to point towards the Earth. So this is to say that the moon is most likely moving this way, right? And it's orbiting the Earth, and it's going to point towards the middle. But because this vector changes, it's going to put a slight wobble or shift in the moon's orbit that we can actually measure here on Earth. Because when we sent astronauts to the moon in 67, I always forget if it's 67 or 69. I think it was 69. But when we sent astronauts to the moon, we had them put these mirrors on the surface of the moon that we can use to bounce radio wave laser beams off of. It's how we're able to measure the distance from here to the moon down to the 1/1000th of a centimeter. Like, we know the distance between here and the moon crazy precisely because of the mirrors that we put on the surface. And you can actually observe the tiny effect that the sun's gravity has on the moon's orbit. Now, here's why I actually talk about this. We know that when it comes to gravity, objects have elliptical orbits, or roughly circular for most of the orbits that we end up discussing, just because getting to extremely eccentric elliptical orbits requires a bunch of math that we're not responsible for. However, where on the free body diagram do I put the direction of the moon's motion?
Nowhere.
Yeah, it's not a force.
Precisely. A huge mistake that a lot of people make in trying to answer these types of free body diagram questions is they're like, oh, and if it points this way, the velocity has to be this way. Yeah, if you do that, you've lost a bunch of points, because the free body diagram, that is not the point of it. We're not drawing a diagram of motion here. We are just trying to figure out what forces are there, because those forces are going to be what drives the acceleration of the system. The free body diagram doesn't care what the velocity is. Now, in reality, the moon is doing this as it orbits around the Earth. And that information is nowhere on the free body diagram. Is this okay?
Mm-hmm.
Okay.
Yeah.
So back to our crash course type review, and I believe the first thing I'm picking up with today is centripetal acceleration. Our comments or questions out there yesterday about where we left off? We talked about how Newton's laws, specifically the correct application of 2 in combination with 3, is actually all of the mechanics that we've learned. If you know the vocab and you know the way that forces interact with other parameters, you can show that correct application of Newton's third law the idea that every force has an equal and opposite reaction force, is actually what leads to conservation of energy and conservation of momentum. Now, all of the motion that we've talked about up through here is linear. That is to say that we're almost always talking about an object moving in some linearized direction. Even projectile motion is kind of a version of that. The only thing that leads to the parabola is the fact that we talk about its linear motion in the x direction. We talk about its linear motion in the y direction. And when you fit those together, since the y direction has that quadratic term, it has that 1/2 gt squared, that's what leads to the overall trajectory being parabolic. Today, I'm going to do a review of the the only nonlinear type motion that we have to discuss. Today, we're going to do a quickie review of centripetal accelerations, centripetal forces, and gravity, simply because those two things go hand in hand. They are both a type of non-linear motion where we're going to rely on some different relationships in order to figure out how the motion will play out. And because most of the orbits that we deal with are circular-ish, right? We are going to assume that if you're given a question about an orbit, which I have a strong hunch that you will be given a question about an orbit, simply because in my brain about the AP test, and this is not a guarantee, this is just my own thinking, they have two questions with which they are going to try and test all of your knowledge of AP Physics 1 up to the point where they ended the content, right? Which means that both of those questions need to be very clever, compound questions that can hit on multiple things all at the same time. And so if they were to do that wisely, that would lead me to believe that one of the questions is probably gravity plus circular motion plus maybe one more topic. I could easily imagine a world in which they mix together circular motion with gravity with conservation of energy maybe. And so it's really common that you see the overlap in these two topics. And that means the other question would also be some sort of compounding of other topics. My guess is conservation of momentum with a little bit of circular motion or something. Does that little bit of preamble make sense?
Mm-hmm.
Okay. So let's go ahead and talk about circular motion and gravity. And notice each one of these little lectures we've been doing is like a week and a half of lecture all compressed into, one 40-minute period, which is why this stuff is so fast. It's because, you already know the big topics, or ideally you already know the big topics, the overview. This is just a chance to get one more chance to look at everything and talk about everything. What are we at? T-minus 3 weeks before the test?
Yeah, 3 weeks.
Yeah, 3 weeks.
Mm-hmm.
Oh, which, by the way, at the same time you guys are taking your AP test, literally 2 days afterwards, I'll be taking my comprehensive exam. So we'll be having bad test times together. Nonetheless, here's the deal with circular motion, and I'm not going to go back through the derivation because any derivation you see of this is messy and ugly. The Cartesian one is messy and ugly. The calculus version of it is a little bit better. It's a little bit cleaner. I think the only good-looking version of the proof of centripetal acceleration is the linear algebra version, the version that you can invent with matrices. But we're going to ignore all of that and just jump straight to the point. No matter what, circular motion requires the presence of a force. And not just one force, not like you set it in motion and now you have the circular motion that you want. It actually requires the presence of a constant force. And this is due to the simple fact of Newton's first law, NL1. What does Newton's first law say?
If the net force is 0, then the velocity is 0.
If the sum of the forces is equal to 0, then the change in velocity is equal to 0. This is just the fancy math lad way of saying, if it's in motion, it'll stay in motion. If it's at rest, it'll stay at rest. But the thing about it staying in motion is that when we talk about motion, we actually mean velocity. So it's not enough to say like, hey, this thing has constant motion. It's always moving at 10 meters per second. 10 meters per second, does that describe a scalar or a vector?
Scalar.
That describes a scalar. And is velocity a scalar or a vector?
Vector.
It is a vector. It has a vector direction. That's why it gets to wear this very cool hat. Cool hats are important to me. If you make a video game and you put cool hats in it, I will be there. I will give you 99 cents for that hat. But nonetheless, we have our cool hat, right? And so if I have an object with no forces acting on it, and here's its initial velocity, but I know at some later time it might have the same speed, but now it's pointed this way, right? This thing has changed direction. What is required to change the velocity?
Constant force.
Some kind of force. There must have been some kind of force, which is the same as saying some kind of acceleration, to take this vector and turn it. You must have had some bridging acceleration here multiplied by the amount of time it was applied for, so that you can go from here to here. So no matter what, changing the direction of velocity absolutely requires the presence of an acceleration. To turn a vector, that requires a vector. Now, the thing that leads to this formulation is rough, so again, I'm not going to go through it, not the interesting part, but this acceleration is called the centripetal acceleration. So A sub c here is going to be equal to v squared over r, where v is the magnitude of your velocity, and r is the radius of the circular path it's traveling along. Like a lot of things that I teach you, this is actually a simpler version of a nastier equation, because if the object was traveling along a non-circular path, if this was an ellipse, there is an equation that you can use to generate the centripetal acceleration there, except it changes over time, because the size of it depends on where you are along the surface of the ellipse. But here, this a sub c can just be written simply this way. And which way does it point? Crucially, which way does it point?
Is it inwards?
It always points towards the middle of the circle. And this is a new thing that I'm going to mention. Technically, that means that the vector direction doesn't come from the velocity. If you take a vector and you square it, you actually remove its vector information. If I knew that this vector was 4 and I squared it, what that's actually telling you is that if you took the area of that vector as a square, that area is 16, and that area doesn't have an inherent direction. So where does the vector direction come from? Here. It points towards the middle, and what do we call that direction towards the middle of a circle?
The radius.
That's the radial direction, and opposed to that, we have the tangential direction as well, which is tangent to the circle. So technically, the best way to write this is like that, with the vector hat on the radius. That's what tells us that the centripetal acceleration always points inwards. And according to Newton's second law, if I take acceleration and I multiply by mass, what does that give us?
Force.
So if I multiply both sides by m, that would give me the centripetal force. Then this is equal to mv squared over r, where again, r is giving us our radial direction. So over here, here's my circular motion pathway. I have an object whipping around a circle. And so I'm going to put my velocity here. That's the way we're moving. And velocity is tangent. Just to review back to geometry, if a line touches a circle at one point on the outside, it is technically tangential. And then in the middle here, we have the radius. So this right here is the radial direction. This is r. And this is also the exact same direction as the centripetal acceleration and the centripetal force. So I'm going to say that if this is my radial vector r, the centripetal acceleration is parallel, and so is the centripetal force. These are all parallel. We're right here. This is centripetal acceleration and force. Is this okay?
Mm-hmm.
Okay. Now we have a second idea, a fake idea, an idea about a fake force. if we go ahead and we think back all the way back to the old times, the before times when we were able to drive and go places, we met up on campus and I filled a bucket with water and I whipped it around. What was the deal with that? If I move my bucket quick enough, what doesn't happen?
Water.
The water does not spill out. That force holding it in the bottom is not a real force. That is actually the Newton's third law, action-reaction pair to the centripetal force. So I'm pulling the bucket inwards with my hand. That's what's putting the tension on the bucket. And if the bucket applies a force on the water, then therefore the water does what?
Stays in the bucket.
It applies a force on said bucket, and that force happens to be outwards. That's what holds the water inside of the bucket. So the word centripetal applies to the force driving the motion, whereas the centrifugal force is a fake force. It's not real, but it is the fictitious force which holds things in, which, I'm going to put it this way, which pushes things as they turn. It's not a real force, which is really big. You are not actually having a force applied on you. And I think one of the easiest ways to like kind of mentally visualize the effect of the centrifugal force is when you're in a car and you take a turn too fast, or you take a turn at a normal speed in my case, right? So light is green, you come up to a turn and you make a right turn across a green light. So, you know, it's your right of way, it's good and safe at about 35 miles an hour. As you make that right turn, what do you feel happening to your upper body?
It's like getting shifted.
Yeah, and if you make a right turn, which way does your body get shifted?
Left.
You get shifted left. Now, you make that right turn, you get shifted left. That is one application of the centrifugal force, but we must appreciate that this force is not real. Here's how to think about it. We're in a car turns right, but you feel a force to the left. All that this actually is that your body tends to want to travel in a straight line. That's what it is to have mass. That's what it is to have inertia. So while it feels like an invisible force is pushing you to the left, what's actually happening is that as you round this turn, your body had a forwards momentum before, an MV, and at this point, you still have that forward momentum, even though the car seat and the friction that has you interact with the car seat is turning. And so it feels like you are being pushed to the left, but all you are actually experiencing is the effect of a rotating frame on your linear inertia. Now, while the amount of fictitious centrifugal force is equal to the centripetal force and acts in the opposite direction. So basically, oops, sorry, should be an absolute value there. So whatever amount of centripetal force is acting on you right here, right, the same amount of force will act on your body on the outside, but the centripetal force points inwards towards the middle of the turn, and the centrifugal force always points outwards, away from the inside of that turn. Is this okay? Okay. And just so y'all know, this principle of rotation in order to create fake force is really important as we move into a future with widespread space travel, because it is a huge problem to not have gravity in space. On the International Space Station, they float around on the inside of that giant smelly locker room all the time. And what we found is that, like on Earth, right, you have a gradient of pressures in your blood. When you stand up, the same way that gravity pulls you down, gravity pulls more blood down into your legs and feet and leaves less blood in your head and brain. And that our bodies have evolved on Earth to take advantage of this fact. This is why your legs use more blood than your brain and eyes do, right? And we found that when people spend long periods of time in microgravity, like they do on the International Space Station, you start to get really nasty negative health effects, because by not having enough leg in your blood, or sorry, enough blood in your legs, you start to get chicken leg syndrome, where the muscles in your legs waste away very rapidly, which is why we have all these fancy setups where we basically tie people with rubber bands to hold them against a treadmill so that you can still walk around in the ISS and keep up with your exercise, but it's not great. Also, people who come back from space need glasses, even though they didn't need them their whole lives, because your eyes have a certain amount of blood pressure behind them. And when there's no gravity, suddenly they have this extra amount of blood pressure behind them, leading to long-term negative effects on your eyes' lenses. So a common design that's been put forward is the same way how, like, I swing a bucket full of water around in a circle. If you make a spaceship, which is circular, and we use rockets to set it in motion and have it rotate, then if you are inside of this spaceship, you will experience a fake gravity. So this is kind of the future of spaceflight for long-term stuff. If you want to have people get to a place, and that trip takes months, like here to Mars, that injection orbit could take anywhere from 4 to 8 months, depending on the time of year that you take it. By having these rotating shuttles, in each one of these pods, if you get the speed just right so that the centrifugal acceleration is 9.81, it would feel like you were standing on Earth. And by having this setup, it can prevent a bunch, oh, I'm sorry, I totally skipped the good part. Yeah, so that means that the ship is constantly rotating. By having the ship be this way, this could avoid a bunch of the negative long-term health effects that we observe in people who spend long periods of time in microgravity. This setup would theoretically let you lift weights in space so that, you know, you can keep those gains up even on your way to Mars.
Mr. Robinson,
Yeah.
do you get taller in space?
You do, because you have less compression acting on your spine.
Oh.
Yeah. But, you know, it goes away as soon as you get back to Earth, so who cares? Okay,
Wait,
is this
Mr.
all right?
Rob?
Yes.
Wait, you know how, like, as you, like, get older, like, your back, like, the discs and stuff, there's, like, a lot of pressure on them, right?
Mm-hmm.
So, like, if you were to go to space, would a lot of that pressure be relieved and you would have less back pain?
It would be relieved, but going to space introduces a whole host of additional health problems. So, like, sure, it would alleviate this one symptom. Oh, heck, I just used a compass to draw the circle. Where's the hole for the middle? It would relieve a whole bunch of symptoms, but I think it would introduce additional problems that you would then need to mitigate.
Okay, thank you.
Okay, so here's a conceptual beatdown on the topic of centripetal accelerations and forces. I have this object A. I don't know what it is, but it is rounding this turn, right, with a velocity v. And it's maintaining a constant speed, but technically the velocity is changing because the direction itself is changing. And we know that to pull this off, there must always be a force, a centripetal force, acting pointed towards the middle of the circle. And the force of C must be equal to the mass of A, v squared, divided by r, where r is the radial length from the edge of this circle to the center of this circle. And all of this to work out must be in units which agree. So if this is kilograms and this is meters per second and this is meters, we get force in units that we like. However, the reason why I bring this up and have you draw this diagram is that it's crucial to understand that centripetal force is not fundamental. There are only 4 fundamental forces in physics, and I'm not going to notate that because it's not a topic of this test. There's only gravity, electromagnetic, strong and weak. However, when I say that the centripetal force is not fundamental, I mean that in a problem. If you were ever asked a concept question, you're like, hey, we have this motion. What force is driving the motion? If you say centripetal force, you have a major gap in your understanding about how this works. Let me give you a couple examples, and then this will be it for the day. And please keep in mind that tonight you have that free response due. We're going to go over that tomorrow for our lecture. That'll be our tutorial. And it has free body diagram stuff, gravity stuff, and circular motion stuff, so we can practice everything we talked about the last 2 days. Let's say we have an object, and we have a centripetal force, which I'll just call force sub C. So let's go ahead and say that object A is your car. And your car is driving in a straight line, and then we take a turn. What is allowing your car to turn? What is the source of the centripetal force? Uh-ohs. You take a car and you're going in a straight line, and so you want to go right. So what do you do to the wheel?
You turn the steering wheel.
You turn the steering wheel, and back in the day, that used to be connected directly to your front 2 wheels, and it would turn those. But nowadays, it's all computerized and motorized, and you have all sorts of fun computer systems in between, like traction control. But fundamentally, the act of turning that wheel is going to turn the front 2 wheels of the car. And what is that going to redirect about those 2 wheels?
The direction
of the what force? How do wheels
Inertia?
push your car? Inertia is not a force. Inertia is what mass measures.
Friction pushes your car.
That's the one.
Yeah.
So for your car turning right, you turn the wheel, it turns the 2 wheels that touch the ground, and by redirecting the wheels and changing the way in which they interact with the ground, it is redirecting the tire friction. This is to say, if you were going to get into some calculation about this, a car turning, the centripetal force is not a force. It is not a force in nature. It is a force that is required for circular motion to exist, but the force doing the circularness of this, the force making us go, woo, that's tire friction. And so if you were going to do a setup or do some kind of solution, your tire's friction is literally equal to your centripetal force. This is to say, it'll be the mass of the car multiplied by gravity, multiplied by mu. This is just the force due to friction of a tire. And this is assuming you're on a flat surface. This is going to be equal to your centripetal force. It must be this way. They are the same thing. The centripetal force doesn't exist because there is circular motion. Circular motion exists because some kind of centripetal force is present to drive it. Let's say that this object A, and this is a callback to the warm-up, is the moon. The moon goes around the Earth 13 times a year. What makes it do that? Why does the moon do this, where the Earth here is in the middle?
It's orbiting.
What is the force? What makes it do?
The gravity from the Earth?
Gravity from the Earth. And so, because the thing driving this orbit, the thing allowing circular motion to be present is gravity, you want to do this calculation? That's great, you do it. Except it's going to be G, mass of the moon, mass of the Earth, divided by r squared. This is just the equation due to gravity. And this must necessarily be equal to the centripetal force, ma v squared over r. And again, this is your setup. You know that the centripetal force is being provided by gravity. They are the same force. And this equation will tell you how this object plays out over time. Or, where we had our lab, I have a ball on a string. And we're just whipping it around because our teacher told us to. And we're going to take some notes. I would review that lab if I were you. It's a good lab. But we have a ball on a string and we're whipping it around. What is that? What is holding that ball in motion? Why does the ball continue along a circular path? What force points at the middle?
Centripetal acceleration.
That is not a force. That is what is here that is making it circular. But if you have a ball on a string, what kind of force does a string provide?
Tension.
Oh, tension.
Tension. Got a ball on a string? It's going to move in a circular pathway because of the tension acting on it from the string. And so you would need to learn information about what provides that tension, and you would set that equal to ma v squared over r. This ain't a force. This is an equation that lets us figure out what is happening with this circular motion, how is it being driven, what's the deal. But no matter what, this force has to come from somewhere. Even when you talk about like electricity or electrons in a magnetic field, if you have the Earth's magnetic field, B, and space radiation comes in from outer space to kill you, it won't. Instead, that radiation will get driven to the North Pole or the South Pole, where we get the aurora borealis. Y'all know that the aurora borealis is caused by the Earth's magnetic field?
Is that the light thing?
Yes, the
Okay.
northern lights.
Yeah, the northern lights. Okay.
Yeah, so the northern lights are tight. They are the result of electrically charged radiation coming from space interacting with the Earth's magnetic field. And the tightest thing about this is that if this radiation came from space and the magnetic field wasn't here, that radiation would just like hit your DNA and now you have cancer. But the Earth's magnetic field protects us from that space-borne radiation by redirecting it to the North and South Pole. A nice consequence of having a magnetic field. Even with this, even if you don't know what is driving this, what I'm telling you is electrons spiral in a magnetic field, which is to say that even for this electron, if it's going to go in a circle, that is because of some magnetic force on it, magnetism. And when y'all go on to learn additional physicses, you will have an equation for that magnetic force. And if you want to figure out, yo, how is this electron going in a circle? What's doing this? That equation of motion is just the mass of the electron, velocity of the electron squared divided by r. It's exactly the same everywhere. Anyway, that's my piece for today. Y'all do your best doing that free response and be sure to get it uploaded online. I'll take grades for it tomorrow after we go over it in the form of a tutorial. Y'all have a very nice day and I'll talk to you on Wednesday.
Thank you.
Bye. Thank you.
Bye.
You are welcome.